the IR, you must have a very clear picture about the circuit connections in your mind first. Remember what's the frequency of the IR? 38 kHz, right? Doesn't matter how many pulses do you have for during that 1 bit. Like if it's 1200 bits per second during that 1 bit, how many pulses do you need to make it happen? It actually doesn't matter. So the IR is like this. Remember what's the duty cycle we are using for this example? Is 10%. And here's the frequency, 38 kHz. Okay, so there will be a lot of these pulses, but how many are there of the pulses are required to make it happen? Doesn't really matter. Okay, as long as you have, I don't know, more than 10 or something, and it's being sent to the air, and the decoder is going to receive it, and eventually the decoder will, whenever there are pulses, it responds with what? 0. Okay, and if there's no pulses, like just 0, and the decoder will respond with 1. That's how that works. And the decoder has an output, right? Think about that. The pulses are being sent into the air, and the decoder receives it. The decoder has 3 pins. 3.3 volts GND, and here's the output. So it receives all these radiation, the IR light, the pulses, and here output a digital signal like this. So this one is being received by the microcontroller, right? And here's the pin. The thing is, how could you communicate with this output? So that's something we need to figure out. And we are trying to use UART. And in your data sheet, you can see the name of these modules are called USART. USART, whatever. But we usually just call it UART. Don't want to confuse you guys. Okay. And your microcontroller has a USB, right? The USB has RX and TX. It goes through the chip and eventually, right? And then here's your laptop. All right. So whenever something's being sent and being received, and we don't have a display module like an LCD or LED module on the board, right? There's nothing you can display the whatever is being received. So, but we know that we have USB connected to the laptop, so we can directly relay all these whatever being received and send it to the TX of this UART and through USB, so we can look at what has been received by the decoder through the UART serial monitor, right? And so now we have to figure out what is this port and what is this port. This is also UART. Okay? And this could be UART, could be something else, doesn't matter because this is the digital signal. You could even just write a soft UART by yourself. Like you are detecting because this pulse, right, so it was high, and whenever it's getting put down, you can detect this falling edge, and then you skip this 0 bit, and then you delay for a certain amount of time because you know this is 1200 bits per second, for example. Okay, so you can definitely program this one by yourself. So you can customize this baud rate by yourself. Okay, and you can detect it and then delay for a certain amount of time and then sample again, and delay a certain amount of time and sample again, delay a certain amount and sample again. You can do that, definitely no problem. And whenever you can use a little index over there, whenever the index is more than 10 because this is first one is the start bit, and then this is the 8 bits in the byte, and eventually whenever it's done, you have a stop bit. You put it up, so there are 10 bits. Whenever you finish all the 10 bits, received all the 10 bits, you just put it together, and that's one message. Okay, so you can definitely program that by yourself. However, you can imagine that it takes a lot of energy and time. All right, so it's called soft serial. If you search online, there are libraries available online, and if you directly use that, there might be issues because you don't know what's really behind the scene, right? It could use a different interrupt which conflicts with the interrupt you are using, right? That could be an issue. So the best way is to customize everything by yourself eventually, so you know what's really happening, right? So you can, if you know that you are using timer 3 for the interrupt, and you know that's being used, right? So it doesn't include any of the public libraries, and it only has a function, just one-liner. It uses the interrupted timer 3 behind the scene, but you don't know, and there's a conflict. You program it, doesn't work, then you stop, right? So for here, task 1, we are going to use, also for task 2 and 3, we are going to use UR1 for this pin, because this data from the output of this guy is a digital signal, and we can program these pulses to form a certain frequency. For example, this one, like this, right? And the red one here for task 1, right? This guy, we can just we can turn on a series of pulses of PWM, and we turn it off. Then we turn it on and turn it off to form a digital signal like this, and make it exactly 1200 bits per second. So that's the signal comes out from the decoder. And then if this one is being shorted to the serial, keep in mind it's UR1, which means it's a hardware, okay? It's a hardware instead of the soft serial. You are not sampling and delay by doing the sampling through the coding everything into the software. However, you are directly using the hardware as a digital block, and you guys are taking embedded system, IPGA in the spring, so you'll learn how to use Verilog to write a digital block, can directly receive the UR signal by the hardware instead of C code, right? It's different mechanism over there. So if we're using the UR1, that's the hardware. Keep in mind, that's the UR1 hardware. It's a digital block already fabricated behind that pin. If this is RX, right, so UR1 RX, and there's a TX, but it's not being used, right? Since we're not sending through UR1, it's just UR1 RX receiving the decoder's input, and it's because this is a hardware, so it's able to detect that pull down event. The pull down event, whenever it pulls down, okay, the digital block inside the microcontroller knows it, and it starts sampling the start bit first, and then the following byte, and then stop bit. So every single bit is being read and put into a register, or you can use a list to store all these digits, and you store it over here. Okay, and then whenever the user press the Shift R, it's receiving, right? So receive it, and it will be able to, so just during that R event, the case R event, right? You press the Shift R in the case R, it received it, but at the same time, it send everything to the serial monitor through TX over here. Okay, one quick question, really simple question. How do you send something through a variable in your C code to the serial monitor and display it? What's the function being used? To be used?
Print F.
Yeah, because if you are there's a specifier, right? Otherwise, just a print, a serial print, right? So serial print send variable through the TX to the monitor. You don't have to do anything else. It's really simple. So in your setup function, you need UR0 because this is already on the board. You cannot change it. That's the UR0 RxTX0 module. It's already physically shorted to the USB and eventually goes to the laptop, right? So that is why I cannot use UR0 anymore. I have to find out another UR module. That was at the very beginning of picking up the correct chip to be used for this class, and we used the Arduino Nano, which is a cheaper one, probably $1 or less, right? So that one only has one UR module, so we cannot run this experiment. I have to switch to the Arduino Mega, which is like $17 per chip. Pretty bad. So this is UR1, but there are more UR modules. Probably, I forgot, 3 or 4 modules, different modules. So we are using UR0, which is already physically shorted to the USB, and we picked up UR1. So you are expecting RX1, TX1 over here. So you have to find out the pin number, the pin name, which is RX1, and then short it physically to your decoder's output. Okay, that's how that works. That's all the hardware connections for this experiment, and nothing else. So the question is, can you change the baud rate of this digital output easily? Oh, it's called baud rate, which is how many bits per second, right? So the baud rate is used for UR only. I've never heard about that being used for other communication protocols, because it's only for UR. So the typical one we have been using, remember when we initialized the serial begin, is 9600 bits per second. I can tell that actually the UR is really old communication protocol. It's really slow, right? It's really slow. And you can pick up faster rates. There are different options. So in your serial begin, you can choose faster ones, slower ones, doesn't matter. But when you change the baud rate in your code, you have to change that in your serial monitor. There's a little option at the bottom. You have to change that one accordingly. Otherwise, it's going to reporting really weird symbols to the serial monitor. So in that case, if you want to choose, this one is all totally customizable, right? If you do that, where do you change the baud rate of serial 1? It might be just one very simple function, right? So Arduino IDE allows you to do that, which is serial 1. Keep in mind, it's 1 dot begin. So in your setup function, you can initialize that by doing this. Okay? And this function will modify the baud rate of your UR1 module, the digital module here, and there's a register controls the baud rate, like other registers we have been using for the PWM, for the timers. It's a very similar thing, right? It's a register. You put a certain digits in there, and eventually it changes the baud rate. So if you do this, it's going to change the UR1 module's baud rate, and because you programmed your PWM in this way, in this manner, right? So you can totally customize the baud rate of your PWM, it's on or off, okay? So pulses, remember the pulses through the emitter, from the emitter, will give you a 0 or 1 from the decoder. 0, okay? It's given, just memorize it. That's how we use it. Pulses being received by the decoder responds with a 0, okay? And you give a 0, you do nothing, right? Don't send anything, do nothing, and the decoder will directly put up. The output will be put up to 1. That's why I drew it this way, okay? See, pulses, you got a 0, okay? 0, you got a 1. So you can have a timer, like determine when you want to turn on the pulses of the PWM, and when you want to turn it off to form this baud rate. So there's a certain way of turning on off the PWM. So I explored that a little bit and find out it's not simply writing a 1. Remember let me turn on just open up the tutorial first probably. This one. Here. If you search on Google, probably you are getting answers regarding how to turn off the the PWM or just output a 0 of it. It tells you that, hey, you can directly just write a 0 to this value because this value determines the on time. Right? Actually, it didn't work. Spent a lot of time on it. It didn't work at all. So, but there are certain ways to turn it off, which works really well. It is this guy. So if you do this, just one line, okay, just one line, it will turn off your PWM. It's gonna output a 0. Okay. So in that case, if I need a 1 for my serial, for my RX1, which program do I need? Which, it's just this guy, right? Just this line, right? If you write this line in there, it turns off the PWM. It's not doing any pulses, not emitting anything, and your decoder is gonna output a 1. That's how that works, okay? It's gonna output a 1. So decoder just does that job for you. If there's no pulses being received, decoder will output a 1. Okay? So you can imagine the 1, remember the for the UR protocol, 1 is what? 1 is the stop bit. Okay? So whenever all the data bits are transmitted, you just want to put up to 1 to finish the transmission. So eventually you need to do that. That's at the end of the program, right? So you start sending the data, the start bit, which is this guy. Okay, that's the start bit. Because this whole block, the whole thing here, you have to if you're not using ISR, like task 1 is not using ISR, you have to manually turn on, turn off the PWM every time. So what you want to do is, if you look at what we planned here, right? So it's actually really simple. Even though the code sometimes looks confusing, right? You turn it on, then you turn on the timer. It's going to be a different timer, right? Because timer 5 is controlling this PWM. So you have to use another timer. So we are using timer 3 for the example in task 1. Okay, doesn't matter. You can use timer 1. Doesn't really matter. So for example, we are using timer 3. It's very similar to timer 1 because timer 1, timer 3, timer 5, all of them are 16 bits, right? So they are very similar. So I turn on. Remember the module I showed you, the 3 lines. That one turns on the PWM. Okay, I do that. Okay, I do that first. So I turn it on. Then I turn on the timer. Okay, turn on the timer. Remember how to turn on the timer? Throw the CS something, right? The prescheduler to it, so it's getting turned on, and then directly assign a value to the TC and T3, right? So the value is stored in there. What's next? It's the overflow, right? It's the overflow. So it's gonna be while it's not overflowing, semicolon. So wait there, right? And whenever the timer is up, it jumps out from the while loop, and then you clear the TOV3 bit by what? By writing a 1 to it. Remember the weird code, right? By writing 1 to it. Okay, and then turn off timer 3. How to turn it off? give all zeros to TCCB3, TCCR3B0, right? Give a 0 to it. Remember this this routine, right? So the timer, how to turn on timer, turn it on, give a value to TCNT, while, right? And clear the TOV3 and turn off the timer. That's it. So you turn on the PWM like this, use that piece of code I provided in the tutorial, turn it on and do the timer thing, okay? And then turn it off and then do the timer thing again. That's how you form these pulses. So these pulses will be sent in that manner and eventually will be received by the decoder as a UART signal by following a certain protocol. That's how we do it. Okay. Let me look at the in class. Make sure you guys can finish that one first. Where we are at right now.
Kind of all over the place.
Okay.
8.
8.
Yeah.
Okay. So that's just perfect timing because we just talked about how do we create that 1200 bits per second, right? The timer 3, we're using timer 3 to do that. Okay? Because this guy here, this this duration is how long? 1 over 1200 second. Okay? So you know the time, and the prescaler is what? It's probably 1, right? It's not changing the prescaler, just 1. And you know the time, you know the counting frequency, which is 16 mega. It's not difficult to find out the count, number of counts, right? Any question on this? Here's the time. And you know it's 16 mega counts per second. So how many counts do you need? How many counts do you need to make this time duration happen, right? And number 9, if you do timer 5, it's to create a 38 kHz PWM output. What is top register? The top register is ICR5B, right? And what is the top value? The top value here. There's an equation for that, right? There's an equation to calculate it. This guy. So we know that the PWM should be 38 kHz. So this number is given, and this is 16 mega. And this is a prescaler, which is 1, right? You use this 16 mega divided by 38 kHz and minus 1. That's how you calculate the top value. Is that clear? Okay.
Can you say that again?
Yeah. So this guy is 16 mega, right?
Yeah.
16 million. And this one is the desired frequency for the PWM, which is 38K, 38,000. And N is 1. Okay, N is 1. The prescaler is 1. So to find out top, which is ICR5B, you just do a simple division over here, calculate it. Number 10, to create a 10% duty cycle for that, for problem 9, the OCR5B should store a value of 10% of your ICR5B, right? If you, in problem 9, if you calculated ICR5B, which is something, and then you divide by 10, so to find out the value for OCR5B. Because the duty cycle is determined by the OCR5B. Right? OCR5B. And this is ICR5B. What is the code snippet to turn on PWM? It's given. This. So LED on here, I had a define on the top of the code, right? So this is OCR5B. You just calculate it. Okay, you can replace LED on with a number, which is fine. Okay, but we are using mode 14, right? So you have to do this and this and this. That's a block. Okay, that's a block of the code to turn on PWM. So every time you are trying to turn it on, you have to copy and paste everything over here, all the three lines. And whenever you want to turn it off, you just copy and paste this guy. And number 13, do you need to manually clear TOV3 when ISR is used in the code, and why? That's something you need to know, because sometimes if you don't have ISR, we have to manually clear it. However, it's not just for the Arduino microcontrollers, it's for PICs as well. I believe it's for STM as well. It's just a very universal concept, right? So if you have ISR, the TOV bit is being cleared by whenever it enters ISR, it's getting cleared. You don't have to manually do it. That's one of the benefits of using ISRs. So whenever you can, just use ISRs. Don't manually code everything up. So task 1 is just manually code up everything, so you can feel the pain first. So in task 2, we are trying to avoid it. Whenever you start using ISR, you can find out it's just so much easier. Okay. So it makes sense, right? Because whenever it enters ISR, which means it already overflows, and you need the ISR to be entered again next time. So definitely you want to clear it. So that's why ISR will automatically clear up that TOV3 bit for you. How to enable that timer 3 interrupt? We have done this in the midterm exam. It's pretty simple. Number 15, in UART transmission, which one pulls down the voltage down to 0 as a start bit? TX or RX? TX. So TX pulls it down, right? Pulls it down. What's the difference? I mean, just one line, right? TX is shorted to RX. What's the difference? Physically, they are shorted together. If TX pulls it down, RX is going to sense that 0 volts, right? So the difference is when the digital designer, whoever works for microchip and designing all these Arduino chips, right? So they wrote all the Verilog, the hardware description language, to design the TX and RX modules, right? So they have to make sure that TX does that pulling down activity, and RX is just using a state machine to detect it instead of pulling it down by itself. So that's the only difference. But it's just one wire. If this pulls down, this one will feel that, will sense that 0 volts as well at the same time. It's just one node, just one voltage, right? Number 16, also the same thing, right? So whenever the transmission is done, the TX is going to pull it up to 1 as a stop bit. Number 17, what's the length? It's actually 10, right? So 10. So TX has to send 10 bits, even though the stop and start and stop bits are not really being used. You can program it. You can not just detect it, right? If this is getting put down, I do something, but you don't really place that start bit or stop bit in your transmission or receiving buffer, because they're not data. It's all the same. It's always 0 and 1, right? Start with 0 and stop with 1, but they're not data. But it's still 10 bits, right? Still 10 bits. So there's a 1 byte for the message and 1 start bit and 1 stop bit, right? For question number 17. Number 18. Which UR module is used for the Skyboard's USB port? 0. Okay? You can always find it from the schematic, right? You can look, start tracking down to that pin. A schematic. It's very helpful all the time. So where's the USB? It's over here as a USB, right? And all the other ones are just the power supply and grounds. And these two are data transmissions, are for data. And it goes to this chip. This chip is a small surface mount chip that give you a hard time when you soldered everything in the first 2 weeks, right? So that's a little one. And then you come down to this point, you can see it's a TX LED, RX LED. So these two LEDs are very helpful. And when you are doing the error transmission, you are pressing the sending commands to the microcontroller, you'll see these guys are blinking because they are either transmitting or receiving. So these LEDs are very helpful. If you didn't have a correct polarization for these LEDs, you couldn't see it. So make sure you flip it or fix it. Okay, so these are pretty helpful. And these are not for data. These are just for blinking. Whenever data is being transmitted, they will blink to show you that, hey, something's happening. And these two lines are the data. You can see RX and TX, right? So RX and TX. So this chip is a USB to UR converter. And it's not, because UART is not USB. They are very different actually, even though they are both serial. But the USB protocol is 100 times more complicated than UART. I just pull it down, then you got data being transmitted. That's too simple. And USB can transmit data at a way higher frequency, but it's just more complicated. So RX and TX, and it's reaching these 2 points. It's PE0 and PE1, right? PE0 and PE1. And then you start looking for PE0 and PE1, they're over here. Okay? Eventually, these are the same name, will physically short them together, even though in the schematic they don't physically short it, but actually they are, because they have the same name. So P0 is shorted to here, P1 is shorted to here. I can see there are TXD0 and RXD0. They are UR0 modules. And there are more than 2 UR modules that I can tell. So I picked up UR module 1, and they're over here. Okay, these 2 wires, and especially RX, right? So RX is pin 45 actually. It's a PD2. So it's the RX. Since we are not using TX1, right? TX1, because the decoder is sending signal to that to my controller. So my controller is only receiving; it's not sending anything, right? So that's why we only use RX1 of the UR1 module, and it's PD2 or pin. I think it's 45. So let's come back to this point, this map. RX1. So it's pin 45 from the manufacturer, from Arduino, right? However, whoever designed the board, they renumbered it as number 19, and Kai put these correct numbers, these numbers on the board. So you wanna try to find out pin 19, and that's RX1, right? That's RX1. So what about the decoder? The decoder's output is which pin? PL5. Okay, so PL5. Is it confusing? Why this? So this seems like this is already shorted to PL5. Where's PL5? Here. What is this? This is like a PWM 5C module. 5C module's output. PL5. Okay, here's PL5. Let me zoom in. Here, the PL5. It seems like the decoder is shorted to PL5. Does that matter? See? Now schematic. This is right shorted to PL5. It's not the UR RX. It's not the input of the UR. Does it matter? It's fine. You just jump it. So you just put a jumping wire on the top of this guy, of this pin. Find out PL5, which is pin what? Pin 44. So you can look at the board. There's a label on it, right? Pin 44. So you want to have a jumping wire, female to female, from 44 to where? 19. What's happening? So you are shorting the output of the decoder to where? To RX1. Question number 19. When we change RX1 to this baud rate, would it affect the baud rate of 9600 bits? Why? That's a really simple question. So it doesn't, because the 9600 bits is set up from the serial dot begin. Parenthesis 9600. That's for UR0, right? There's nothing to do with UR1. There are two different digital modules. Is there a conflict, do you think? What is UR1 doing? UR1 is receiving data from the decoder's output, right? And you save it into a variable, and then you just take time to send it back to the serial monitor. That's it. There's no conflict. So the expected results look like this for the first one.
All right, tutorial 5, task 1. So if I press S, enter.
Give me a second. Let me change the resolution real quick. This guy. Still pretty small for this example.
5 was just sent, and so 35 here is the hex number of the ASCII code of 5. And I do another, so I'm going to resave it, press R here and enter. So 5 was just received by serial 1. Okay, and then do S one more time. 6 was sent, and R receive a 6, send a 7, receive a 7, send a 8, receive 8. Up over here, and the reason for that is
so it's very small, but you can watch it on your computer, and you'll be able to tell. So what's being done for task 1 is I programmed the number in there, a letter. It's I just put a number 5. You can put whatever you want in there, right? It's a character. I just put a 5 in there, and you can add a 1. You can add a 1 to the character, so it's actually adding to its ASCII code, and you can keep outputting 5, 6, 7, keep adding right to it. So the first time I press S, the case S, it's gonna send. It's gonna send the stop bit, right? Stop bit and start bit and data, and then stop bit. So the byte is actually the ASCII code of the 5, of number 5. So that's the message, the byte being sent. And then I press R, it receives it, and then print it out to the serial monitor. So let's see what is given here in the code. This time, this could be a little bit challenging because I didn't give you a template. Instead, I copied and pasted everything, a lot of things in here in the tutorial. So I have to start doing all the define and declare all the variables by yourself. So this one, you will need the following block as a routine to create a time delay using timer 3. So here's the timer 3. When you turn it on, right? You turn it on, you do this. followed by this. That's the timer 3, delay, to create the time delay. And if you turn it off, after turn it off, you also want to do this immediately. Okay? Because this time delay, it's gonna give you a time of 1/1200, right? And for this part, it's using a mask. So the thing is, how do you determine which 1 or 0 to be sent? For example, letter 5, right? Or just a random hex number here. Random hex number here. 0x, it's a byte, right? It's a byte. ASCII code is a byte. 1 1 0 0 0 1 1 1. Right? It's a byte, something like this. Okay. So the way to do that is you can use a mask. You can use a mask and shift your mask. So the mask at the very beginning is this guy. 0 0 0 0 0 0 0 1, right? That's the first mask. You do an AND logic, you could do a bitwise AND. And then you can see, because this is trying to detect your LSB of this byte first, right? That's the letter to be sent, right? That's the letter to be sent. If you do an AND logic bitwise AND, and this is giving you what? All the other ones will be cleared, right? But only this is giving you a 1. So this eventually becomes a 1. Okay, so you can do if the result, okay? If you don't do anything, which means if the result is 1. Okay? If you want to see if this is 0, you can do this, right? Explanation in front of it, but let's just do this. If this result is a 1, and then you send the 1, how do you send the 1? Turn off the PWM and put a timer. How do you turn it off? Here. TCCR5A. And then the timer block. Where's the timer block? Is over here. This guy, right? The timer block. Oh, this guy. This guy. Okay? So here's the timer block. Timer 3 block. Then else. For example, it's a 0, it's not a 1. What's the result? It's gonna be a 0, right? So that will falling into this category. So the else, what do you do? Because you detect a 0. You detect a 0. So if you detect a 0 for that data, and here you want to send a 0. Okay? If you want to send a 0, should you turn on or turn off the PWM? Turn on, right? So how to turn it on? So that's the block. Here's a block to turn it on. Right? PWM on. Block. And then do a timer 3 block. And you also need to check, because every time you do that, you shift your mask to the left by 1. See here? So this little 1 will be shifted to the left by 1 bit. So next time you do an AND logic, bitwise AND to that data, the data bits is not changing. So your 1 next time becomes here, right? You shift it to the left, so it start detecting the second bit, right? Then you do it one more time. If you detect 1, you do which one? Which one? Detect 1. Which one? This one or this one? If you detect 1 here, you are sending a what? Hey, the data is 1. The data is 1.
Then you do the first one that's on feedback.
Here. Because the data is 1, I want the decoder output a 1, so your IR need to output a 0, right? So you need to turn off your PWM and set up a timer. Just keep doing that, and eventually you check if your mask is reaching 0 or not. You can see here you are using a while loop. If the mask is not 0 yet, then you do this, right? If it's 0, which means your 1, the little 1 here, already shifted out through the MSB. So because you are keep shifting this guy, eventually the 1 will be shifted out, right? And then it becomes 0. So are using this one, so while mask is not 0, you just keep shifting and keep detecting, right? If it's 0, you stop. You jump out from the while loop, then do what?
Then you probably need to reset the mask.
No. Yeah, but anything else?
Stop it.
Yes. How do you stop it?
Send a 1.
It's not a send 1. It's a turn on the PWM, right? It's this guy. So whenever the mask is 0, you want to jump out from that while loop. Then you turn on that PWM again to send a stop bit, or to let the decoder output a stop bit to put that up. So the UR1 will detect that stop bit. Then you're done. Okay? So that's the main part of the code. Probably covers 80% of it, and the rest is pretty simple. And the R is given, right? So R is given. So what's happening is whenever you press S, it starts sending out data, and the UR is really simple, right? So it's actually trying to detect using this function, serial1.available, to so if something is being received and this function is going to return a 1. So that's why you are detecting this one. So if this guy is larger than 0, which means that I received something, and so it returns a 1, it detects it, right? And then it starts doing this. So serial1.read, parentheses, this will return whatever being received by the RX, and there's a little register behind that pin. So that register is a byte, it's going to receive your byte, and then you directly place it into a received this variable, and you can start printing this out. Okay, so the format is not super important. You can see it's already given. It's asking you to print it out, you know, the original data, and also the hex version as well. But that's less important. You can eventually figure that out. It's not a big deal, actually. And for the S part, I think this is the major part of the S part, right? And you need to put a start bit as well in front of it, because this one, whenever you get a mask start rolling, it will start detecting every single bit in the data. So you need something in front of it to give a start bit, which is basically just put it down, right? Put it down, you need to turn this on, right? You need to turn this on. So start bit, you need to turn on the PWM, so it's able to put it down to ground to start it. That's a UR protocol starting point. Okay. We'll talk about task 2 on Wednesday, and you can watch the video and see what's being expected, what are the expected results. Also task 2 as well. And task 3 is just way more complicated, and we'll start working on that on Friday. Okay. But you can start programming this already. It's pretty much already given, 80% already. So don't wait until the last minute. Okay. That's it for today. What's up? Turn on in class number 8, please. Turn in.